interpolating strings like a boss. I can't generalize interpolation like a boss yet. So hello everyone. Thank you for coming, despite me not being on the schedule. I think this is payback from what I did at Scala World, where we had about 25 speakers back in September, and I didn't tell them when they were speaking until 4 a.m. of the first day of the conference. So Alexei has paid me back. I mean, he wasn't one of the speakers, but nevertheless, he's applied the karma, and he told me this morning I was speaking. So I have this talk about interpreting strings like a boss, and I'm going to take you through a number of different levels of working with string interpolation. Now, I'm sure everybody is very familiar with the most basic string interpolators. Some people have probably used more advanced ones. By the way, would you just give me an indication whether you consider yourself sort of beginner level Scala? Is anyone here a beginner? So Miles, Paul, okay. Does anyone consider themselves sort of advanced? So you're all liars. I'm sure you're. Yeah, we'll see how we go. The first third of the talk will be very straightforward, very much familiar Scala. It does take a turn to the more advanced for the second and thirds, but hopefully you'll sort of follow along. If you don't understand what I'm talking about, I'll share the slides later, and hopefully you can just go back and sort of make sense of it. But we're going to start at the beginning, the value level, and with a very simple example, which I'm sure you've seen things like this before. We have I have a laser pointer. We have what looks like a literal string here, prefixed with the letter S, and we substitute this string here, boss, into the position here indicated by the $. There's nothing difficult yet. We can go slightly more advanced, and we can actually use braces to put an entire expression in here. So interpolating. Now, can anyone tell me what this says when you actually run the interpolation? Interpolating java.lang.strings like a boss. Maybe we can do better than that later. We'll see. But I mean, you can see any Scala expression can be substituted in that position there. So this gives us quite a bit of flexibility. S is just an ordinary. It's one of potentially many string interpolators. We can give them any name we like. Any identifier can go there, and I'll show you how you can choose them later. Now, what you saw there gets translated in the compiler to maybe more familiar code that existed before these were introduced in Scala 2.9-ish. So that on the previous slide will be transformed during the parsing phase of the Scala compiler. It will transform it into this. We have a new string context object created. This is a case class with parameters, which are always string literals, and they're the bits of the string that are known at compile time. They're the constant bits. We exclude, during the creation of the string context, we exclude all the variable parts. And then given that object we've just created there, we apply the method S to it. Now S is basically the text, the identifier, whatever that happens to be, that appears prefixing the string literal. So here it's S, and then we apply parameters to this, which are the variable parts. So a key distinction to make is there are the fixed bits here, here, and there is an empty string at the end. Don't forget that. It will always be there. Well, it might not be empty, but in this case it is empty. But there will always be a string constant there. And then there's the variable parts which get slotted in. Now, it's an important point that this happens in the parser. So keep that in mind for later. So if you wanted to write one of these, if you wanted to write the S interpolator, we would maybe define a method that would meet this application here. We want to define this method S. So we do def s. Now this takes var args of type any. You can substitute any type into the SInterpolator, and you can have any number of them, and any number of values can slot in there. And this will take the CTX is the string context. We get the parts. That's the name of the value containing the fixed parts, and we use the intersperse method, which has one serious disadvantage I'll explain in a second. The intersperse method to slot the variable parts in between that, and then we just call make string. Okay? And that will produce a string at the end of this. So the return type of this, although I haven't included it, will be just a string. The disadvantage of intersperse is that it doesn't exist. So you have to write something like this. You have to, first of all, make sure that you have, what we're trying to create here is a list of lists. We want to make sure that the two parameters here are the same length. Now, you've got sort of fence posts and fence panels here. We have to add an additional one to make sure they are the same length. So we just prefix the empty string here, and we're going to use the transpose method and then flatten it. And then what that actually does is it sort of puts pairs them up, puts them in rows, and then it reads those rows as columns, and then ultimately what you get is all of these things in the right order. There are probably dozens of different ways of doing this. You could zip them. You could write a while loop and append them to a string buffer. These are all possibilities. This, I think, is maybe the most concise, but maybe not the most intuitive. But pick your poison. Hey.
How much of that executes in the compiler, and how much is at runtime?
So this is all happening at runtime. So this is an ordinary call to S. The compiler has translated the string context code you write in your source to an application of this S. So it's just like calling the method at runtime. The creation of the string context object as well happens at runtime. So a new object is allocated to the heap, and so on. Now, to make this work, we need access to the string context. And the string context is a class in the Scala standard library. We can't modify it. We can't magically get an S on that object, but we can add an extension method here. And we use an implicit class. Now, who here is familiar with this implicit class? I don't want to call it a pattern, but this way of adding extension methods to objects that are defined elsewhere. I think most people are sort of putting their hands up at different points, and ultimately, everybody's at least familiar to some extent. Good. So this is how we make it work. This is sort of the standard way of making our string context, making that application of the S on a string context work. Without this implicit class in scope, we can't do it. Now, this is, after the translation in the parser, this is a very ordinary method application. It's dumb. The translation does not know anything about the types involved. All it knows is that it's got this thing that looks like a string literal. It's got a little prefix, which is some alphanumeric characters, and it's got some expressions which slot in. This happens in the parser. It has no more information than that. So it doesn't do anything intelligent. The transformed code is subject to all the standard rules of Scala, all the type system rules that would normally apply, because it happens before it hits the typer. The typer is where all the interesting stuff happens in the compiler. So we can define that method in any number of different ways, provided it sort of meets the requirements for that call to .s, or whatever it happens to be, to work. So the parameters don't have to be strings, they don't have to be any, they can be a type of your choice. It can return things other than strings. It can return unit if you wanted to. You could make it side effecting. You can do all kinds of things. There's nothing to stop you doing this. It's entirely orthogonal. You could overload the definition of S. You could have a version of S that takes one parameter and returns a string. You could have one that takes two parameters and returns a double. And this will work as if you had written the transformed code directly into your source. What people typically do is use var args, because often you want to substitute multiple things, but that's not necessarily the only way of doing it. This method could have type parameters. You could infer a type. You could instantiate a type in the method application, which depends on the parameters that you substitute, or the types of the parameters. You could add implicit parameters. So remember, it is just a call. It can because the source code looks the way it does. It doesn't matter if there's an additional implicit being pulled in. The actual application will look the same. Now, consequently, we have some unintended consequences. So I'm going to leave this here for 30 seconds or so. Can anyone tell me what is happening here? This will work in a fresh REPL. If you start up Scala now, type this in, this is what you will get. Is anyone thinking, what the hell is this?
String context already has equals.
So, say again?
String context already has equals.
So equals is a method which exists on the string context type. Good. Now we're substituting a value which is itself a string context into this. Now, remember this desugars into creating a new string context with the constant bits, which happen to be an empty string there and an empty string there. So what this is essentially saying is string context, empty string, comma, empty string, dot equals, and then the one parameter here, which is the variable part, which is string context. This is a case class, so it has an equals method defined, and they are the same. So we get true here. I posted this on Twitter, and people were a bit shocked and confused by it. Someone came back with this. This also works. And a lot of people didn't like it. Didn't like the fact that you can write code like this, and it looks weird. I like to think of it as orthogonal. Like, should we have another rule which says, well, actually, these special methods, these methods, I'm going to special case them and say these are forbidden in a string context, but everything else is fine? Or do we just have the simple rule, the transformation is consistent every single time, it's dumb, you don't ever second guess it. Some people didn't like my orthogonality claim. I think it's debatable. Whether it makes the language simpler or more complex to... or maybe, I don't know if any of you went to Bill's talk last, which I don't know if that would explain the difference between complexity and simplicity to make a judgment on this. But it's not for me to say. So that's sort of the introductory level. It's going to get a little bit more complicated now. So we're moving to the type level. And I want to talk a little bit about the motivations behind this. Why do we want to do any experiments with these string contexts? Now, if any of you have been to my talks before, at least one person here has been to this exact same talk before. Thanks for coming twice, Miles. Oh, sorry, yeah, Miles did miss the first half of the talk last time, so I'm expecting him to leave probably halfway through. Or anyone else is also welcome to leave halfway through. So all of my talks are basically the same. They are making it harder, making your life harder as a programmer. There are ways to make your life harder as a programmer to write code that doesn't work. That I see as my role in life, to make your life harder if you're trying to write stuff that will fail at runtime. And we have DSLs everywhere, and it's a common part of what we do as Scala programmers. And there's this question: should we externalize those DSLs? Should we put them in separate files? Should we parse them at runtime, or should we embed them in the Scala code? And can we take advantage of what's probably the most complicated step, the most I don't want to say intelligent, the smartest step probably in our build process, which is running the Scala compiler. Should we take advantage of that to use all the knowledge we have available during compilation to add additional constraints? Now, this is a possibility with these sort of DSLs that we can put in interpolated strings. So I'm very keen to take advantage of this information because more constraints is always a good thing as far as I'm concerned. So here are a few examples from, mostly from Rapture. So we can have a URI string context. Now in Rapture, what this actually does is it reads the first few letters, the bit before the colon, and decides what kind of, what type this should return. This one returns an HTTP URL. But if you put file in there, it will return a file, so we get a different type at compile time. The methods I'll show you later will maybe not directly explain how you implement things like this, but you can sort of take the ideas and work out the various possibilities. We could have CSS. We could define things like properties like color, line height, or whatever else you get in CSS. And we could guarantee that the name here is a valid CSS property name. If you accidentally put a U in color, which I do all the time, it would be a compile error. You would not accidentally deploy that to someone's web browser ultimately. We can do XML checking. We can check that this foo here matches the foo here. Same again with JSON. Rapture JSON does this a load, and we can check that this is well-formed JSON. I've got a shell command interpreter, so it will we can sort of put some variable parts. We put a file there, which is a parameter to the WC command, and then we execute that, and we expect to get back an integer. So we're sort of constructing here a command. We're not running it, but we can then later call .exec on it and get a particular type out. That's just a nice convenience method for farming work out to the underlying OS. Email addresses, it's pretty straightforward. It can check with a regular expression there. And we can even have things like numbers with units. We can check that that's a number. We can check that that is a frequency we recognize. And we could say that these two values are actually equal. So we could have them. We could have these checked at compile time, and it can know that the combination of the killer modifier here means that this is actually the same value. These are the possibilities. Now, I'm going to give you an example of why this, I think, is particularly the compelling reason I sort of put a bit more thought into this recently. I was working on the Scala World website. Scala World is a conference I ran in the UK a couple of months ago. And I was working on the website, and I'm not a web designer, I should say, but I sort of approached the task of running a conference as a Scala programmer by just sort of doing all of the things that are required in the sort of most Scala way I possibly can. And I was writing some CSS, which is a bad start to begin with, but I was doing the development work, and at some point I deleted a closing brace in my CSS. So it wasn't valid CSS. And essentially what that meant was that the second half of the rules in my CSS, I don't know how many of you have had the misfortune to have to write CSS, but the second half of the rules that were in the CSS file suddenly were no longer applied, and the result was that the website looked like this. Now, let me talk you through this. This is Miles's dog. This is John DeGose, who was doing training. This is sort of the venue. There's some text here and indeed everywhere that talks about the conference. These are the rules that were in the first half of the file. They worked. Like I said, I don't consider myself a natural designer, but it's sort of strangely beautiful in a kind of dark way.
Very Hieronymus Bosch.
Right. So I thought, could we actually do better than this? Could we have Scala read CSS? I don't want to design a DSL that is sort of has all the properties of CSS, but requires me to sort of add capital letters in places and apply native Scala syntax to it. I want to just copy paste my CSS into the code and sort of add constraints. And if I've got some HTML in the code as well, I want to be able to link the two. I want to know that if I've got a class, do you want me to go on to a different slide? Can we get rid of it? There we are. I wanted to take advantage of being able to cross-check a load of things in the compiler. So this was the motivation. I fixed that just in time for the conference, but it did waste some of my time. So the string context we've seen. Well, I showed you at the beginning the S string context. And these are the ones we're most familiar with. These are the ones we see a lot of the time, and they're very weakly typed. I mean, they did take a number of any parameters, and they return a string. Whereas we would possibly have the criterion that we would rather embed just some subset of types into there. Now, one discriminating factor we would maybe use is if there's a corresponding type class to this particular type, I would like to be able to embed that into the string interpolator. Any other type, I want to be a type error. This is a sort of typical use case, and I think it applies in many of these cases. We may actually want different types interpreted in different ways. So depending on the type, we may want it to substitute the value that is effectively the toString, or we may want to, for example, put quotes around a string. We have different requirements depending on the type. So I'll talk a bit about embedding. I'm going to use this word to mean embedding a particular type in a string, an interpolated string. So say we've got our CTX. This is going to be our new string interpolator. We can put an S in there, foo. That makes sense. We can substitute a string. We can substitute an int, I. We want that to work. Whereas this one here, where we substitute a future, what does that mean? What would we ever intend that to mean? Now, I can write a type class that substitutes strings. I can write a type class that substitutes or embeds integers. But I'm decided I'm not going to write one for futures. Now, maybe they look like this. So we've got this embeddable type class. Who is fine with type classes? Who is not fine with type classes? OK, cool. If I'd asked that question 2 years ago, I'm sure there would have been more hands up the second time than the first time. So I've got these definitions here. They're not very interesting. I'm just calling toString on the int, and indeed just returning this is effectively the identity function here. We can write this in Scala 2.12 like this, which is a whole lot more concise. This is using the SAM feature that's just been released a couple of days ago. We can put a lambda on the right-hand side, and provided the expected type is something with a single abstract method, which indeed this one is, it will automatically wrap that in creating a new one of these. So that's a really neat way of doing it. I would encourage you to do it, but it's not what this talk is about. Now, given that we want to have an embeddable type class associated with the types we substitute in here, maybe a really naive way of doing this would be to define context as having some number of t is an arbitrary type. We're using varargs, and just get an embeddable type class that corresponds to that t. Now, could anyone tell me the problem with this?
You know, all ints or all strings.
So yeah, so it works where all the t's happen to be the same, but when you have a mixture, for example, like this, list of 1, 2 as a string and 3 as a double, what's the best common supertype of those? It's any. And what it would effectively do is resolve the type t to any, and it would look for an embeddable of any. We don't have one. So we need to do something a bit better than that. And this is my approach to doing it. I think you can do it with shapeless and hlists and a macro. I can do it without a macro. So what I'm going to do is to find this embedding, what it will effectively do is for each parameter, it will tie together the value that you actually place in the parameter position with the corresponding type class. So every single value that gets put into that method call will have the type class pulled in, different one potentially for each different value. This is, so it's creating a new embedding. That is where it pulls in the embeddable type class, and that is the value. That's where T comes from. That's where it knows which embeddable to get. And we end up with an instance of embedding. And indeed here we ask for values, varargs, of type embedding, and the type here is existential. So they can be different types. And what we do is we map the apply method, so we can write that very concisely like that. Apply is defined as basically getting the type class, this one here, and calling embed on it. So this is a neat way to tie the two together and avoid difficulties with lubs. So this will now work. It'll get different type classes for each of these. This will not, because I never defined one for double. And we'll get a type error at this position here, and it'll say can't find, it'll say type mismatch. But you'll know at least where the error is. Is that kind of okay? Is anyone uncomfortable with that? Don't be shy. Okay. So I thought, well, that version works for the embed method. That's just one particular type class. So I thought I'd write a more general version. So I'm inventing this thing called annexed. It's a generalized version of the embedding here. So I'm gonna take a type class which is a higher kinded. This is a type class type, so it itself takes a parameter, but we're not going to specify what that parameter is. So this might be something like show, if you're familiar with show from cats. We've got the type of the value, and then we're going to be able to access the value and access the type class from an instance of annexed. Oh, my battery is running low. This could be a disaster. Is there a power outlet nearby? Yeah. Thanks. Just mind plugging it in. Thanks. Okay. Hopefully we are all good. And we have an implicit which actually creates a new one of these. So if it sees a value of type T, it creates a new. And it needs an annexed of some type class. It will apply. The Scala compiler will realize there's a type mismatch, and it will apply this implicit, which you can see most of there. I think that's pretty much all of it. And it will create a new annexed. And what's probably the best thing for me to do is show you how you use it. So forget embedding, we're going to use annexed now, and I'm going to ask for varargs of annexed of the embeddable type class. Remember, this boilerplate around here is just the bits we need to make this into a string context. And then given the values here, for each one, we're going to call .embed on it. Now, this is like a lambda within a lambda. The implementation, if I go back, I didn't show you this slide before, is we've got this sort of double lambda here. What it's saying is effectively for each value, we call apply on each one, which itself takes a lambda, and that lambda is the method we want to call on the type class that has been resolved for that particular annexed value. Now, all of these, because embed, in our earlier example, always returns a string, even though the types of all the annexeds vary, they're existential, we end up with a consistent type at the end, so we end up with strings here. You can write it like that. I would write it like that, but anyone I worked with would probably dislike me a little bit more for it. So what this means is that we can now write things like interpolating strings, like a job role. That works fine. This will fail unless we have an implicit defined for dealing with embedding classes. And this is exactly what we want. So this little trick, you can actually, there's no reason why this wouldn't apply to other methods that are completely unrelated from string interpolators. It's just particularly useful in this example. We have a bonus level. That's the end of the type level, by the way, but there's a little bit more type level stuff later, but now we're going to go for a bonus level. I was up late one night reading the Scala source code in bed. As I have trouble sleeping. Very good, very good. And I was reading parsers. I was actually looking at the source code for how these string contexts are created. And I noticed this little comment here, documenting that it is intentional that the ident is not rooted for purposes of virtualization. And there was another line of code which was commented out, which was effectively the code to modify the AST to insert a root.scala.string context. But that was commented out, and instead it was inserting a string context. So not root.scala.string context, which is completely unambiguous. It was inserting a new string context. So the transformation is indeed exactly as I described it on the third or fourth slide. It's not creating the exact class you think it might. It's creating a new instance of whatever happens to be called string context and is in scope at that time. And this is intentional. So of course this got me thinking, what could we use this information for? Because I mean we've got the implicit class method. We can add extension methods, and we get that functionality. But one thing implicit classes can't do, you can't use an implicit conversion to convert something from some type to a dynamic. It will not. So by the way, who has not seen or heard of dynamic in Scala? Some of you are looking at each other and say, dynamic, what's that? But you're not putting your hands up. Has everyone seen, you haven't seen dynamic? Oh, so dynamic allows you to call a method on an object in Scala. If that object inherits from dynamic trait, you can call a method with any name you like, any identifier, and it will compile. And it will compile to a call on that method to a method, on that object to a method called selectDynamic, which passes the identifier, the supposed method name, as a string literal. So it's sort of lifting from what appears to be a method that you expect to exist to a string literal with that name. So I use this in Rapture JSON to sort of have some JSON value .foo. There's no method called foo defined, but it works as if there's a. I mean, it's like a JSON object that will try to access the foo key in that JSON object, and it works fine. I mean, I quite like it, and I probably use it more than most people do. But you can't do an implicit conversion, so that I mean, if you could do the implicit conversion, then you could actually have all method calls. You could convert from all T to a dynamic, and then you could just call anything on anything, and your Scala would suddenly become an entirely dynamic language and would fail. But how about we create a dynamic string context, and we call it string context? That's the important thing. If this is in scope, we can define apply dynamic. This is the name of the method call. So for an interpolated string, this is the prefix, so I might as well call it prefix there. And then this is the arguments that get called on that method. And I'm going to do a really, really simple implementation here and just return the prefix, whatever that happens to be. I'm going to completely ignore the variable parts, and I'm going to ignore the constant parts. And it means you can write this. You can write anything prefix, any prefix, then an empty string, and then it'll create that. Apparently, I've only got 5 minutes. Is there someone following me?
Yeah.
Oh, okay. I thought I was the only person in this slot. So let's rush through level 3, the macro level.
Were you able to come up with a reason to do that?
No, Miles might have thought of something since we discussed it.
Emphasis on discussed.
Yeah.
I think the problem is that the last character of the prefix has to be literally adjacent.
Yeah. So you can't stick a space between the prefix and the opening quote. I mean, what you could do is have like a different kind of symbol in Scala that instead of starting with a single quote, always ends in a double quote. But you're welcome to come up with better ideas for this. So I will rush through this macro level, which is probably the worst thing to do because it's the level above the type level. Imagine we want to embed values in JSON. We've got an f value there. That would make sense if it's a string or an int. That's fine. But I mean, we could write that or we could write that. And when we substitute that value in, if it's there, if it's a string, then we want to put quotes in as well. If we replace that with the string in quotes, then we end up with too many quotes and it ceases to parse. So how I would describe this is that the context of this whole is different in these two examples. And you could even imagine something like this, where you could, if f were a pair from string comma string, then maybe this would make sense. But I mean, we're treating it differently in each case, and this is obviously something more complicated than simple string substitution. So let's do this with macros, because why not? And remember, like I said at the beginning, this string contexts are all orthogonal to other features of Scala, so there's nothing to stop you implementing this with implementing the method with a macro. So if you remember, this would get translated to something that looks like this. We're going to pretend that we still got all the annexed stuff. I would implement this JSON with I've got this toJSON type class, and I'm going to get varargs of annexed of that. So any type that has a toJSON type class can be substituted in there, and we will implement that with a macro. And the approach, which I will sort of go through very quickly, because I don't want to make this a talk about macros, least of all in the last 3.5 minutes. What we will essentially do is take advantage of the fact that we know that the transformation that happens in the parser will be consistent all the time. It will always be the same shape, and we can match on that AST. It will look something like that. These will be the literal values, the constants, the constant strings. At compile time, we don't know we know what the expressions are, but we don't know what the values of those expressions are. But we can lift out the literal values there. They will look like this, literal of constants, and they will be typed as strings. So essentially what we do is, at compile time, we have access to the values as just a list of strings of the constants in our string interpolator, interpolated string at compile time. And then the macro can use that. It can parse it, it can check it, it can throw compile exceptions. It can give you warnings. These are all useful things you can do with it. I'm going to skip all the type level stuff, unfortunately. But you can do some interesting things with H-lists and singleton types. Here's our code sample. Now remember, this gets desugared to the string context. And this is what the implicit does. It calls annex on f, and remember the typer is looking into this. It sort of works out that it needs to apply the implicit value there. By virtue of this implicit being found, it knows that the type parameters to annex are these, and this results in a typed value here. Now this is all sort of an example of what the compiler is doing, particularly in the typer. And it knows all of this information. It knows that the value here is a string. Now, I won't really explain how, but we can actually get additional information in there as well. We can define our type classes so that we know that the context for strings being the context for strings being embedded into JSON can be some type, some phantom type. With seconds to go, this is the wrong time to be explaining phantom types. Now we can use that information to make something like this work. We've got a string, we've got a pair, a string and an int, we've got another string there. This can be checked at compile time. It can know that the context of this substitution here, means that the way they get put into the code is different. We can know that pair, by virtue of the type class that is resolved, can be substituted in position here, but could not be substituted here. I mean, this is code that should compile. So we can do all these checks in the macro. It can do some very interesting things, and we get more safety. I'm making it harder for you to write bad code. One last level, the boss level, which I tried to explain at Scala I/O in Lyon a couple of weeks ago, and realized that I lost Miles. He was my last remaining person who understood everything up to that point. I lost him there, and I realized actually I didn't understand it either. I discovered this the day before I went to Scala I/O in Lyon. The day before I visited EPFL in Lausanne, which is a couple of hours away. And this was a terrible mistake, because I went to see Dennis Shabalin. And the worst thing you can do when you've got a sort of almost finished talk is go and meet someone who knows more about the subject than you do. And I had a chat, went to his office, had a chat with him about it, and he said, well, you can do a load of other things. You can do pattern matching. And he showed me how you do pattern matching. Now, you can imagine we've got a string here, and we can write a case clause here, and we can put an interpolated string in here, which has, it's got some content. It's got, I've put this variable name here adjacent to these parentheses. What I want to do is say this is a regular expression for reading an HTML tag, and I want to label this capturing group here, and I want to call that tag, and I want to call this one here text. So you can pattern match on a string. You can get the contents of this one here as tag, you can get the contents of this one here as text, and you can create a new instance from that. The code you need to write to do this is so horrendously complex, and that's a very sketch implementation. The best thing to do is to go to Dennis's GitHub repository here. If you want to take a photo of this, it's very well documented. There's a very, very clear explanation of how you can write this, but it's step by step. And I would recommend, if you're interested in doing this sort of thing in pattern matching on interpolated strings, then it's well worth following that. And that is all I'm going to do on the boss level this time. Maybe in the future I will understand it too, but for now there is that repository, and I'm out of time. I'll say thank you, and there's probably no time for questions. Is that right? Yeah. So thanks everyone.